Okay, so a couple things. I didn't get the test all the way graded yet. I'm about halfway through. I think with only 4 of you, it wouldn't take as long, but there's just a lot of details in OChem, as I'm sure you're aware. So a couple of things that I've noticed right off the bat are common mistakes. Two people got this wrong. It's R, not an S. Maybe 3 people. Put S. I think 2 people put S instead of R, and 1 person forgot to assign stereochemistry at all, if I'm remembering properly. No, 1 person. And then this one, I think almost everybody realized that if you can either count from this way or from this way, you could get 7. What people miss is if you start counting here and go around, you get 2,5-dimethyl. If you count the other way, you get 3,6-dimethyl. So that's a minuscule, I think it was a 1/4 point I took off just for counting from the wrong side. Just keep that in mind. And the propyl is in the same spot either way. It's on carbon 4, regardless of which way you count it. So overall nomenclature was okay. The other thing I would point out is on this one. Remember that the Z is not referring to the carbon chain, it's referring to the bromine, because we use the priority system. So that's the Z. Because methyl has priority on this side and the bromine has priority on this side. If I'd written cis, then it would have been like that, because cis is referring specifically to the carbon chain, but Z is referring to that priority system. A little nitpicky, but just to make sure we're being careful with that. And then the only thing so far that everybody has missed. Yeah. Oh, almost everybody said both tertiaries are going to have the lowest bond association energy, but the allylic tertiary is going to be lower. Yeah. Than, and even the secondary allylic will be lower than the tertiary. That's not allylic. Once, and even when I was writing the key, I did it at first too. And then I looked at it again, like, wait a second, there's resonance here. So always want to pay attention to that.
I also think I said that the sp2 carbons I said were secondary, but that's not a thing. Right?
Yeah, I didn't mark anybody down for that, for saying these are secondary, because they are both connected to 2 other carbons. Technically vinylic carbons are not considered secondary because they're not alkane, they're not sp3. So we would actually just put them in a separate category as vinylic instead of secondary. But that's nitpicking, and I didn't put that option up here, so I didn't mark anybody down for that. And it does get down to semantics. I think that there are some textbooks that would say that that's a secondary vinylic carbon, and some that would just call it vinylic. So it depends a little bit on who you're reading. Anything else I wanted to talk about? Hey, everybody, if you missed anything on this one, you probably figured it out pretty quick once you went back and reviewed your vocab. So we don't need to spend too much time there. And I'm in the middle of grading reactions, so more to come on that when I finish that. The other, I did it right. I can never remember. You guys know the keyboard shortcut to switch between tabs in Firefox? It's control page up or control page down. It's really, I love keyboard shortcuts, especially when I have 2 screens like this. I can't see what the heck I'm doing on one of them. All right, and like I mentioned, we I forgot to hit publish until this morning on the quiz for last weekend. So we'll do it collectively here. And as long as you hit submit by the end of the day today, then everybody will get a 10 out of 10. I figured nobody would have a problem with that. Oh, that was the other thing about the tests. I think I actually counted the points wrong and there's 6 extra points in the test somewhere. So everybody will just call that a built-in curve. Also grade it out of 100 instead of grading it out of 106. I think I just counted wrong when I was first writing it up. I think is what the issue was. But I'm not going to go back and take points away from any of the sections that I wrote points in. So more extra points. All right, I'm going to put 2 questions on the board here, and then I'm going to go grab a Kleenex for my nose.
Yes, it's just, I'm just.
All right. Once we get the hang of this, we don't even really need to worry about oxidation states, right? We can just look at number of carbon oxygen bonds. And we can look at this and say, well, the oxygen is in the -2 in both cases. So we can talk about it as the entire compound, but really it's this carbon that's reacting that we're worried about. So oxidized, reduced, or neither? Oxidized. Anytime you go from an alcohol to a carbonyl, that's oxidized. That's not going to work as soon as I scroll. So. Oxidized, reduced, or neither? Neither. The carbon still has 3 bonds to atoms that are more electronegative. So that's actually one of the reasons why there's a whole class of functional groups that all get lumped in together because of the same oxidation state. They're all called acid derivatives, carboxylic acid derivatives. So this is called an acid chloride. We basically just take an acid and you replace the OH with a chlorine. Amides are the same thing. So an amide group looks like this. You've got an acid chloride, you can have an acid anhydride, which is basically 2 acids attached to each other. And they all have different levels of reactivity, and we have a whole couple chapters on acid derivatives. But they're all the same oxidation state, which makes it actually pretty easy to convert back and forth between the various acid derivatives. One more I'm missing. Acid anhydride, acyl chloride, esters. So an ester looks like that, where you have something that looks really similar to an acid group in the middle of 2 carbon chains. Again, same oxidation state. All right, so converting between any of those is going to be neither oxidized nor reduced. Christelle, I didn't realize till this morning that I didn't hit publish on the quiz, so we're just doing the quiz together. And as long as you fill out the answers by the end of today, everybody will get 10 out of 10. So here we've got a ketone going to an ester. It's a weird looking cyclic ester, but it's still just an ester. So oxidized, we added an extra oxygen, we have more, and actually, that would actually mean 2 carbons got oxidized in this case. This carbon, the carbonyl carbon got oxidized, and then by adding an oxygen in between 2 other carbons, this carbon actually would get oxidized as well. All right, and then there was some acidity. An acidity question, which of these would we say is most acidic to least acidic? What's the most important factor? Resonance. So two of them have resonance and one doesn't. So that gives us one end of the spectrum, right? But we can right off the bat say cyclohexanol is least acidic. And out of these two, I didn't draw out all the bonds for the NO2 group, but what is an NO2 group going to look like in terms of structure? We have a nitrogen in the middle, obviously. And then the double bond and single bond. That's going to resonate back and forth, right? And that adds up to an overall net charge of 0 because the nitrogen's got 4 bonds, so the nitrogen's a +1, and one of the oxygens is always going to be a -1. So is this going to give us more resonance? Is this electron withdrawing? Is this electron donating? How should we think about this? We're just comparing these two.
My gut says electron donating, can resonate.
Is electron donating going to give electron density into the ring, or is it going to pull electron density out of the ring?
So it's electron withdrawing.
Right, because that means that there's a resonance structure that's going to look like like that.
Right.
But it does give us more resonance structures in general.
Yeah.
So it's electron withdrawing because the resonance structures are all pulling electrons this way. But the fact that we added more resonance structures is going to stabilize our conjugate base. So both of those factors point to this one being more acidic.
If it was in, I forget what the positions were, but if it was in the other position right there, would it still have that same?
Not nearly as much, probably not a measurable difference in the pKa's.
Okay, so phenol will be more acidic in that case.
In that case, we'd probably put them about, which really should be an option for these, so to have. Anytime I do one of these rankings, it's hard to put that into an option you can select on the online quizzes, but if I was asking this on a test, it's always fair game to say I think these two are about the same. And you might miss a half a point if there's a detail you're missing, but you know, if they're close, then I can give you most of the points for that. Interesting fact about nitro groups. Does anybody know of a aromatic compound that has nitro groups on it? The very famous one.
TNT.
No. TNT stands for what?
Trinitrotoluene.
Trinitrotoluene. Trinitrotoluene is really reactive because these anytime you put nitro groups on a benzene, it's going to be really reactive because these nitro groups can basically just pop off and turn into a gas. And anytime you've got a reaction, they can very easily produce a whole bunch of gas molecules very quickly. That's a recipe for something being explosive, right? Because generating a whole bunch of gas really quickly causes an increase in pressure, which causes an explosion. So it's not actually that dynamite itself, it is an exothermic reaction, but it's not actually the exothermic nature of it that makes it dangerous. It's the fact that it generates a whole bunch of gas molecules almost instantly. Which interestingly enough is also true of airbags. Airbags work in a very similar way, except that they don't rely on TNT. Although if you were really careful about how you measured it out, you could. They actually, but because they want it to be started by a chemical current passing through a system. They use I think it's sodium azide. That reacts to generate a whole bunch of gas molecules really, really quickly when it's hit with current. And literally the way that your car airbags deploy is if it goes through enough of it's literally got like a metal sphere that is really heavy and held in place pretty tightly. But if you decelerate fast enough, it rolls to the side and completes a circuit. And when it completes a circuit, it starts the reaction and your airbags explode.
That's clever.
It's pretty clever. And that's why it's also why they're actually really good for very dangerous practical jokes. If anybody's seen those YouTube videos of like car mechanic shops where they like put an airbag underneath somebody's chair.
Yeah.
And when they sit on it, all you have to do to set it off is connect it to a battery. And then it launches them. It'll launch somebody into a ceiling if you're not careful with it.
Ouch.
Very funny. One of those very funny YouTube videos. Very much don't try this at home. All right. Last question here on the quiz. And we didn't get to this question, so ignore this one. This is the first thing we're offset by one lecture from where I was last year. So this was actually a question that we're gonna get into, one of the first things we're gonna talk about today. All right, any questions on the quiz stuff that we did get to?
Are we gonna have to upload for question 5?
No, I don't know, I'll probably just leave question 5 blank. All right, and I'll just put points for everybody there. All right, so today we're looking at the reactions of alcohols, both how we make alcohols and how alcohols react to make other things. Our most basic reactions to make alcohols are going to be our SN2, SN1 reactions, where we have a hydroxide as a nucleophile. We've been doing that for, geez, close to 6 months at this point, right? Or at least it feels that way. But there are some other reactions we can use to do that. And specifically when we look at oxidations and reductions. There are oxidations and reductions that can produce alcohols as the product, or where alcohol is the reactant. So this is why we spend so much time on oxidation states, is we're going to get into a lot of redox reactions with these oxygen-based functional groups. All right, so the simplest of these reactions, if you're trying to produce an alcohol, if we're going to do it with a reduction, we just start with something that's more oxidized. So a carbonyl, if you reduce it, will produce an alcohol. And it's really straightforward reaction. No, there's no rearrangement going on. It's actually a pretty straightforward mechanism as well. But all we wind up doing is you can basically think of it like doing a hydrogenation to a carbonyl. Because hydrogenation of an alkene, we broke the pi bond and we added a hydrogen both sides, right? That's the same net result as what we get here. We can't just do hydrogen over platinum. That technically would be a reduction. We just don't get good yields with that. So that just applies to alkenes and alkynes. So we need a stronger reducing agent than just hydrogen gas in order for this to work. Partly because oxygen is more electronegative than anything else. It's going to be hard to break this pi bond in a reliable way just by using hydrogen gas. Before we get to the actual reagent, so can we make a tertiary alcohol by doing this? Why not? So a ketone gets reduced and makes a secondary alcohol. What would we have to reduce to make a primary alcohol? An aldehyde. We reduce that. we get a primary alcohol, what would we have to reduce to get a tertiary alcohol?
Carbon 10 bonds, statements.
Yeah, exactly. We'd have to start with the carbon with 5 bonds, 10 electrons, in order to do that. That should look really wrong by this point, right? Felt wrong. I didn't like drawing the extra carbon on there. So we can't just use this approach to make a tertiary alcohol, but if we want to make a primary or secondary alcohol, it's a pretty straightforward process. All right, and so I guess I do have, if we go to very high temperatures and pressures, we can get this to work. If I'm remembering correctly, though, it's something like 100 atmospheres at 800 Celsius. If you do that and it's catalyzed, you can get this reaction to go. It's beyond the scope of most labs, though, and there's easier ways. So for the most part, we're not going to use this. And that actually is really handy if we want to, if we have a ketone and we have an alkene, if we want one of them to react but not the other, that's actually useful to know where the limits are in synthesis problems, right? So the most common one that we use is sodium borohydride. We already saw this with the oxymercuration. We use that as the second reactant to reduce the mercury and get it out of there. It's a fairly strong reducing agent, but it's also relatively shelf stable and it's not going to explode generally. Problem with these reducing agents is you wind up reducing things really, really effectively. Sometimes that produces a lot of gas molecules really quickly. So sodium borohydride, if you let it react with a carbonyl, you basically can just treat this as a hydride source. So instead of being an acid where we use it as a proton source, a hydride source just means we've got some, the boron is actually less electronegative than hydrogen. Or they're so close to the same amount that basically when you break this bond, the hydrogen will actually keep the electrons. So you actually wind up with, instead of an H plus floating around, you actually get an H minus floating around. And H minus is going to be attracted to a partial positive. It's a nucleophile, right? What part of this molecule has a partial positive? The carbonyl part has a partial positive, right? So basically, the mechanism is pretty straightforward. Although usually we don't just write it as a hydride, we write it as these electrons moving over towards the carbonyl. We don't leave it at, do a leaving group and then a nucleophilic attack. We do both at the same time.
Would the hydrogen hold on to both of the electrons?
It does.
Yeah.
Yeah. Yeah, not a free radical reaction, so we're not going to have any homolytic. They're not identical in their electronegativity. They're close to the same, and I do think that hydrogen is more electronegative than the boron. And the nice thing about this is that you can do this reaction in a protic solvent. Because your protic solvent really doesn't have a good target for a hydride. We don't really wind up with a competing reaction because if we had, say, methanol does have a partial positive that a hydride could attack, but it's already an sp3 carbon. In order for the hydride to attack here, we would need to have a leaving group leave as well. And oxygen doesn't make a very good leaving group. So we don't wind up with a competing reaction in this case. And that's, if we had a stronger reducing agent, we would have to worry about that. Or if we were doing this under acidic conditions, because if we did this under acidic conditions, we would have this floating around, right? And that's a better leaving group. So under acidic conditions, you do wind up with some competing reduction reactions if you don't pick your solvent carefully. But for the most part, as long as we're neutral or even basic, we don't really, basic conditions will work. But typically we do this in neutral because we want to minimize any side reactions that might happen. And this works for any what are called class, I'm gonna mix them up, class 2 carbonyls. I think are the aldehydes and the ketones.
Is that intermediate or is that just a certain process?
So what would the intermediate look like? Yeah, let's finish this up. So we're drawing this whole thing from the beginning. That first step is gonna look like that. We're gonna make BH3 borane, which is still technically a hydride source, but not nearly a strong one. So it's basically gone, used up at this point. And what do we get here? We broke the carbon oxygen pi bond, and the oxygen kept the electrons. And then the hydride got added to the sp2 carbon to make it an sp3 carbon. And this is why it's really why we do usually want this to be a protic solvent, because what's the next step gotta be? Proton transfer. So whatever your solvent is your most common source of protons. So let's say we're doing this in methanol. We make a methoxide. And we get our alcohol product. And even that, so then once we get this reaction done, we're probably going to neutralize it too, because this is going to produce an overall shift towards a basic solution, right? So that's your complete mechanism for that step. Would it look any different if it was an aldehyde? Not really, right? Because an aldehyde is still just a carbonyl. It's just not a secondary carbonyl, it's a primary carbonyl. All right, so here's the mechanism drawn a little bit more cleanly. Nucleophilic attack by the hydride makes your sp3 carbon with a deprotonated oxygen and then a proton transfer. One thing to keep in mind is we can't do this for carboxylic acids and acid derivatives. This works for aldehydes and ketones. And even aldehydes and ketones aren't identical. One of them is more reactive than the other. I want to say aldehydes are more reactive in this, but I'm going off of memory there, so don't write that down necessarily. There is a slight difference in reactivity between these. But carboxylic acids and acid derivatives are too oxidized for this to work. Right, so it seems like a fairly limited reaction in a lot of ways. It only works for aldehydes and ketones, and it can only make primary and secondary alcohols. But it's a good start in terms of learning these reduction reactions and how alcohols are going to be produced. And this is actually the opposite of what your body does with alcohol. The first step when your body breaks down ethanol or methanol or ethylene glycol is there's an enzyme called alcohol dehydrogenase, which based on the name what do you suppose it does? Dehydrogenates alcohols. So in other words, it turns alcohols into ketones and aldehydes.
That's where you get formaldehyde.
And that's where you get formaldehyde. And that's if you drank rubbing alcohol, isopropyl alcohol, you would get acetone. Also not great.
Yeah.
Ethanaldehyde, so ethanol works, it still makes a toxic byproduct. But it's less toxic than formaldehyde and isopropyl alcohol. And so it's typically with alcohols that are toxic, it's actually the byproducts of the metabolism process. And which is why we can tolerate them in trace amounts. They're not good for you and you'll get a nasty headache. We can tolerate these in small amounts because as your body's breaking them down, your kidneys are also flushing them out as fast as they can from your bloodstream. But certain things, if you actually drank a shot of methanol, it's going to just turn formaldehyde very, very quickly and you go blind is the first symptom of methanol poisoning. I believe ethylene glycol poisoning as well, antifreeze. But it's the same enzyme for all of the small chain alcohols go through use the same enzymes, all alcohol dehydrogenase. And they all have similar effects. It's just all about the relative toxicities of the byproducts. Yeah, so and isopropyl alcohol. If we do the same thing, we're just gonna take that and turn it into a ketone, right? Not really that good for you. It's interestingly enough though, acetone's not good for you. It's a carcinogen, it's poisonous, or toxic is the better term. But your body will actually produce small amounts of acetone naturally if you put it under certain dietary conditions. Anybody know what those are? Ketosis. Which happens when what? You know?
No carbohydrates when you're digesting fats and making.
When you're digesting fats with no carbohydrates, the fatty acid metabolism produces a ton of acetyl-CoA, which feeds into the electron transport chain. But in order to do that from a fatty acid chain, you have to use up some of your NADH that you run out of, I think. Basically, and you wind up with a bottleneck because you run out of NADH because it all winds up being held up in this state where you can't use it in order to make the acetyl-CoA. And so in order to free up some of the NADH so that it can continue on the electron transport chain, your body takes the acetyl-CoA and converts it to acetone. And that frees actually the coenzyme, it's the coenzyme A, maybe that's the bottleneck. I don't know, I have to look at the specifics at this point. But regardless, if you going into ketosis, if you know somebody who goes on a hardcore 0 carb diet for a long period of time, you can actually literally smell acetone on their breath. Because it's a side effect of burning fat, stored fat for an extended period of time with 0 carbs. So even if you're trying really hard to lose weight, you want to have a little bit of carbs because just a little bit of carbs is enough to use up, keep that process going and not get that bottleneck where your body needs to produce ketone bodies. The other one that gets produced in that process I think is methyl ethyl ketone, which is also called butanone. If I'm remembering correctly.
Like a 2-month stint with keto one time at work, it was just really hard. I ate a tremendous amount of salad and meat. Now
Yeah.
it's like veggies and meat. I was like,
Yeah, and it's like you said, it's always a balancing act, right? Any diet's a balancing act. Is it better for your body to lose the weight and become healthier that way, or is it better for your body to not produce these toxic byproducts? The balancing act, if you're someone who's got cholesterol issues and you're way overweight, it might be healthier for your body to go through ketosis for a while and drop the weight so that your heart's not working as hard and you can clear the cholesterol.
it worked really
Yeah.
well. It was like, and it gave me like this kind of mental clarity too. I don't know what it was, but like there was something about that. But it was just hard because it was very limiting. So I couldn't eat some pretty It's really
Yeah,
strong.
and most. I have to, this isn't a nutrition class, but I will say most diets that work, it's about finding, they're always about finding a source of calories that you can live with the cravings for. So if you have a sweet tooth, going 0 carb might not be for you. You might need to cut your calories somewhere else, but it mostly comes down to calories in, minus calories out. Whatever you personally can live without to get that calorie count down is going to be a diet that you might have success with. But everything in moderation, right? Because you completely eliminate any of the major macromolecules, you're going to cause problems for your body long term. Short term, your body can handle it, but not great long term. Back on topic. It's okay. We have time in these, so. We have stronger reducing agents. Sodium borohydride is really handy in that it's not super strong. It's strong enough to reduce carbonyls, but it's not super strong. If you use a stronger reducing agent, like lithium aluminum hydride, it's still just a hydride source. The mechanism is still the same. But because aluminum is even less electronegative than boron, we wind up with it being even more reactive hydride source. So much so that it'll actually it'll reduce water. You basically will wind up taking the water and reducing it and making hydrogen gas. So we don't actually use it with protic solvents in the same step. We actually have to separate it out as a separate step. We have to do the reduction in an aprotic solvent and then give it a proton source. But it's the same mechanism. And so this is pretty useful in a lot of ways. It's not, we don't always want to use that. If we can use the sodium borohydride, we generally want to. Right, so we have a couple ways. There's a couple reasons why this might be helpful. One, if we want to reduce everything, every pi bond, we can do hydrogenation at super high temperatures and pressures. So we can take this heptanone, and reduce everything to get it into being cycloheptanol. If we only want to reduce the carbonyl, we use a hydride source. Hydride source is not going to attack the alkene because there's no partial positive. This is not a great target for a nucleophile, right? So if we use a hydride source, we can reduce the carbonyl without reducing the alkene. And the flip side, the one that's not shown here, is if we want to reduce the alkene without reducing the ketone, we use hydrogen and platinum, but at lower temperatures. And you might get some of this as a product, but most of it is going to react the alkene. The other place where lithium aluminum hydride is useful is that you can also reduce acid derivatives with it. It's a strong enough reducing agent. We can actually take those acid derivatives like esters and amides and turn them back into a more reduced form. It's too big here, but classic Thor meme, right? You can't defeat me. No, but he can. Right, so sodium borohydride is not great for reducing carboxylic acids. It's really handy because it's not super reactive. So it's really easy if all you need to do is reduce an aldehyde or a ketone. But if you need to reduce an acid derivative, then you use lithium aluminum hydride. but I'm gonna come back to this slide in a second. Basically, anything that has an oxygen in it, if you expose it to lithium aluminum hydride, it's gonna reduce it all the way to an alcohol. As long as you have enough, as long as you looked at the stoichiometry and you have enough moles of it. So an aldehyde could be reduced with lithium aluminum hydride, alcohol can be reduced, and you reduce both sides of it. If it's something that we wind up breaking the molecule apart, like this ester, we're gonna fully reduce that carbon all the way to an alcohol, which means we're actually gonna produce methanol as a product as well. We split that ester in half. So it would actually wind up with one propanol and methanol.
Oh, good. This will happen with the board, right?
That won't happen with sodium borohydride. Sodium borohydride would hit this and not be able to do anything with it. What do we get from this one? Is there a carbon on the other side of an ester? No. So we're just gonna take this and turn it all the way to one butanol. It gets a little bit different if it's an amide. Most of the acid derivatives are gonna do the same thing with sodium, with lithium aluminum hydride. Amides though actually do something a little bit different. I believe they actually get reduced to an amine, but we'll talk about that when we get into the acid derivatives chapter in more detail. For now, focus on esters and alcohols. Those are the acid derivatives that we're gonna see most frequently and that are most useful for this. And we get the same product as the aldehyde, right? We just have to do a different stoichiometry. We need 2 moles of lithium aluminum hydride because we're doing for the second one in order to do 2 reductions. We need to provide 2 moles of hydrides to add to the carbonyl here.
Plus that would be for B.
For B, yeah, and we need 1 mole of lithium aluminum hydride if we're only gonna reduce it once.
Why would it not then also just reduce it further into butane?
Because oxygen's just not a good leaving group. If you want to take it all the way to butane, you have to do something like take the butanol, make it a better leaving group, replace it with a bromine, and we can actually use a bromine, we can actually expose to a hydride source and get it to get the bromine to leave, but because the oxygen is not a good leaving group, it'll stop here until we make the alcohol a better leaving group.
Then would it be the same for the ester as having the 2 molar equivalent?
Yes. Yeah, any of these acid derivatives are gonna need 2 moles of lithium aluminum hydride. Although we don't get too picky when it comes to writing them out, if we just, it won't stop really predictably. So we can't use lithium aluminum hydride to reduce it to the aldehyde and stop there. It'll take it all the way to the alcohol, which then we would need to oxidize 1 step to get to the aldehyde. We're trying to do that. Anything tricky about these? Find your carbonyl, turn it to an alcohol. Right, the key is just in recognizing that's a proton source. Or sorry, a hydride source. And then it's just gonna do. You can think of this as being a nucleophilic addition as well. It's another way to classify this reaction, right? The hydride's gonna act as a nucleophile and selectively attack here, breaking a pi bond. Which looks really similar to our acid catalyzed bromination of an alkene, right? Acid catalyzed bromination. It was an electrophilic attack to get that proton transfer to start things. It's the same general gist. You break in a pi bond, and then you're adding something to each side.
The mechanism will basically follow the same as.
Yeah, we have. This hydride, we can bring the electrons over with it. Need to make room. We make the alkoxide ion as the intermediate, and then we just have a proton source to do the proton transfer. We just, if it's lithium aluminum hydride, it has to be written in 2 steps.
Yeah.
Sodium borohydride, we can do it all in one pot. How would we name this? It's really easy to draw these complex molecules, and once you get the hang of it, writing products is not even too tricky. What would the parent molecule be? The longest continuous carbon chain that has the OH. Just one. So this is methanol with a complicated branch. So it would be something like 1-methyl cyclohexyl methanol. This is why we kind of learned how to use the parentheses earlier, right? Remember, I'm like, oh yeah, you can learn isopropyl, but it falls apart when you get to bigger things. Yeah. This is an example right here, because that actually wasn't that hard once we realized it was methanol, the parent molecule.
And as you were saying last lecture, basically everything that we're gonna be going over will have the priority in terms of naming.
Yeah,
So-
so anything that you name with a suffix is gonna be the most important priority from here on out. And that means longest continuous carbon chain with that functional group. It is, well, okay, you can name something if it's. This is where there are competing nomenclature systems to some extent, because you can name as a cyclohexane with a methyl group and a hydroxymethyl group. Because you can name an alcohol with a prefix. We don't typically do that if the alcohol is the most important functional group. But if we did something like that, now cyclohexanone is the most important molecule here. And then we would name it as a cyclohexanone with a methyl and a hydroxymethyl. Hydroxy is the prefix for an OH group. So you can add a hydroxy to a methyl in parentheses. And a methyl to cyclohexanone. Still is going to follow our same rules. We wouldn't, even though that seems simpler to treat it like cyclohexane, because the cyclohexane doesn't have any functional groups on it, it's not our most important part, so we can't name it that. And realistically, the other thing about this is if this is a really important biological molecule for some reason, occurs all the time, or even if it's a really common industrial molecule, it's gonna have. Yeah. You know, yeah, you could name glucose as like some hexal, you know. And with a cyclic ether compound, you could, there's an IUPAC name for glucose. But it's ridiculous because it's glucose, that's what matters, is that it's glucose.
The whole dihydrogen monoxide is in.
Exactly, that's a great example as well. Yes, technically you could name water, it's dihydrogen monoxide, I'm actually a fan of naming it as an acid.
Yeah.
Which would be
Yeah, that's cool.
hydrohydroxic acid.
Amazing.
But that's beside the point, so. It's all about knowing when to stick with IUPAC and then. And usually what I use as the deciding factor is if we put that molecule in MolView and we looked up the information card. Does it give you? Does it give you one methyl cyclohexylmethanol or does it give you a common name? MolView is pretty good at.
Yeah, no, it gives you mostly common names.
If it can, yeah.
Somebody's got those up there, right?
It'll show you both, yeah, but the
Yeah.
one that shows up at the top, because what it does is there's a way of writing condensed structure. For the entire molecule in type form. And it basically takes that and throws it into the NIST web book. Or the, what's the other one? I'm forgetting, there's a couple of databases that MolView checks. And it has this I think it's called the canonical smiles.
Oh, yeah, I've seen those.
And it's basically just a
There's
really
those
long
T's,
text strings,
O's,
yeah.
And dashes.
And it's like SM lowercase I LES or something like that. One of the letters is lowercase. It's some sort of acronym. It basically uses that to query a database. The canonical smiles is easy to copy and paste. But it's not easy for the human brain to parse, to understand what it's saying, so it makes it really convenient to take that and throw it into a database. And see if it matches up with anything, and then it returns whatever the common name is first, usually. PubChem, that's the other one. That either the chemistry web book or PubChem. All right. Anything different about this one? Yeah, add an H to it. Since we're talking nomenclature though. How would we name that molecule? Count them again. There's your longest continuous starter chain. Is not part of the ring, so it's 2-propanol. Is your parent molecule. And then it's gonna be, so it'll be 1,3-diphenyl. No parentheses needed with that one, but I wanted to remind you that when we have a benzene ring, it's as a substituent, we use phenyl as the prefix. Not benzyl. Seems like benzyl, but benzyl's a different thing.
And then if the alcohol group's attached to the benzene, it will just be phenol.
It would be a phenol, yeah.
Yeah.
If we had something done like that, then that would actually be a hydroxyphenyl group. And that would actually be the easiest way to name it, would be still calling it 2-propanol, 1-phenyl, 3-hydroxyphenyl. In parentheses with the number 3, 2-hydroxyphenyl. But that actually wound up being easier than making this the parent molecule and making all of this a complicated chain, that's even messier, right? It's really easy to draw molecules that are really, really painful to make. Turns out. All right, let's take a break. We'll come back, we'll talk a little bit more about reductions. Let's come back at 5 after. We're just gonna be short lab today.
Oh, is that it?
No, we're not gonna start a new lab today. I've gotta get a kid to Kale Community Center by 4 for basketball, so. You benefit from my complicated schedule.
First sunbird of the year. Yeah, so I completely went up to, ground top, let's find some pictures. Where's that? It's in the Coleman Wilderness Carson Pass. Check this out. That's so pretty, there. Oh, these pictures. There's Tahoe. Hanging out there. There's RCC area right there. Pyramid. Give you some yeah, you look see like down to behind camera. Yeah.
Yeah, raise the binoculars or something.
Yeah, it's just phones are wild, dude. And then I always try to, whenever anyone taking a picture of anyone else, I try to get a picture of some of the person taking a picture. Top around top Saturday.
I was about to say that was.
Tahoe.
It's in Tahoe, Gables.
Yeah.
Let's see. Oh, yeah, you can't even see what it's.
Winnemucca is like right down in here, you just can't see it.
Yeah.
It is, yeah, you just can't see it. That's what I'm talking about. Winnemucca is like. It's hard. That way.
I always love staying around top of it. It's such a beautiful, like in the summertime, like surveys.
It is.
Or is it, it's valley, it's this valley is on top.
Oh, man.
Barely any trails going through it. I think like right behind this mountain, there's like a little tiny cabin.
Oh, really?
Yeah, it's a little tiny cabin, it's like really old wooden cabin, and then that's, yeah, their valley.
Yeah.
Or, yeah.
That's what I'm saying.
I like to look at that. And no, so.
But still, then you can see the real summit. We didn't bother doing anything aggressive. You know, it's like it's already missing that. And then so.
But I just wouldn't.
This was just hiking back out, yeah, pretty much out. It's hard to see the back of it. Yeah.
I got on my mountain bike. I kind of not quite satisfied tires.
Oh, okay, yeah.
So I can kind of
Do some stuff. Yeah.
some stuff. It's some parts are too deep on it.
Yeah, slides like spears sometimes.
Little tiny spikes.
To like grab on the bike helmets and shit.
And wood chips.
That was
A bunch of rain chips and stuff. Take off. Yeah, no, it's fun. How do we work it out?
Yeah, and we're just up there. So I wish we got more snow or we got a little colder. It's all, the snow's all rotted. Not good right now.
No,
Up
It's not
above like
great.
9,000, gets okay, but there's not that many places around here.
yeah. Well, and all the backcountry is so tracked out
Yeah.
and
Oh, yeah.
crowded these days.
There've been a lot of baggies lately.
Yeah.
Down in like Mammoth area, it's used to be still.
Especially with like.
It's going over here in like Sugar Bowl.
Yeah,
With the crazy temperature fluctuations. Like that, so
Yeah.
Recipe for
yeah.
snow layers just go by.
All right. Let's look at the mechanism for an acid derivative. So again, just like you were saying before, it's the same general principle. The lithium aluminum hydride is going to act as a nucleophile. and we make an sp3 carbon as an intermediate. So same as reducing an aldehyde. Thing is, it has to do it twice. Because then we have a good leaving group, or at least an okay leaving group. In the form of our, either our if it's an ester, it'll look like a alkoxide as leaving group. If it's an carboxylic acid that we're reducing, we would just have to have OH as our leaving group. It delivers the proton.
Yeah, stop.
So then once we get this first intermediate. This will be a common theme with carbon or with the acid derivatives in general. Is if we start by taking a sp2 carbon and making it sp3, it'll try to go back to being an sp2 carbon if there's a good leaving group. So we make this tetrahedral intermediate, and then it kicks off the methoxide and goes to being an aldehyde.
Yeah. That's.
And then we-
Most of us have the same overlay.
Yeah. And then this then becomes the same exact thing as the sodium borohydride, right? Once you get it to an aldehyde, the reason we can't stop it here though. Just keeping track of the stoichiometry is not enough to get it to stop at the aldehyde. So when you're using lithium aluminum hydride, you go all the way to the alcohol. It'll keep going. And probably because the aluminum hydride, even once it's given up one of its hydrides, it can still act as a hydride source again, because aluminum is so good at giving up electrons. We don't usually draw that mechanism that way, but that's why we don't stop in the middle. Alright, and so then once we have the aldehyde hydride source attacks, we make another tetrahedral intermediate. It's going to stay tetrahedral this time because we don't have a good leaving group. And then the proton source to protonate at the end. Most frequently, we use water for our proton source for the second step, just because it's water. It's easy to use. But there's no reason why you couldn't use ethanol or methanol. All right. And just because I can tell when we're covering things at about the same time as other colleges are covering these topics, because I start seeing an influx of relevant memes to various online chemistry platforms. I liked this one. So, I'm in danger. Basically, but this is a good way to remember it though. If you've got a carbonyl, you see lithium aluminum hydride, doesn't matter what type of carbonyl, it's not going to stay a carbonyl. All right, so here's the other, this one's actually even more useful as a synthesis reaction than hydride reductions. Because hydride reductions still are not changing the carbon structure. This reaction gives us a way to actually change the carbon structure, like with our acetylide ions. So a Grignard reagent. I saw an interesting, where was I? I saw an Italian word with the GN. I think it was at a Mexican restaurant. And to make the pronunciation really clear, they added the tilde over the N. In Italian, the G and then the N implies Nya, just like in putting the tilde over an N does in Spanish. So I just thought that was interesting that somebody actually had written, I think it was lasagna. They had lasagna at a restaurant or something like that, and they wrote it like this, which I quite feel like that makes it really obvious to see what's going on, right? So Grignard obviously was Italian based on the pronunciation of his name. And what he figured out is you can, if you take a bromide but pretty much any alkyl bromide, if you expose it to metallic magnesium, you make this weird intermediate where you basically insert the magnesium between the carbon and the bromine. So a little bit like the hydroboration step, where we basically inserted an oxygen in between the carbon and the boron, once we added our oxygen source. Basically, it just inserts itself in between there to make, this is what's called the Grignard reagent. When you take a bromide and you add a magnesium to it. So obviously we're not gonna name, there's no common IUPAC designation for that, so we just call it the Grignard reagent. Or we just call it magnesium phenylbromide or magnesium propyl chloride. So it does work, we see this most commonly with bromines, but it does work with chlorines as well. I say that we see it most commonly with bromides, but the chlorides work as well. And what that does is it kind of does the same thing that a hydride source does. It turns this carbon into a nucleophile. Because now we have a carbon in a covalent bond with something noticeably less electronegative than it is. So same logic even as the hydride sources. For whatever reason, magnesium works better than aluminum or boron in the case of carbons. So we see specifically magnesium used. But then once we have this, we get a strong partial negative on the carbon that's directly attached to the magnesium, and now it's a nucleophile. Because not only is it a partial negative, this is a really good leaving group. The magnesium bromide is. So you can see how this winds up being really, really helpful because one, it doesn't do rearrangements. And if you can put a bromine or a chlorine on a carbon structure that you then want to add to something else, this is a really convenient way to do that, to add, and instead of doing it 2 carbons at a time using acetylene or needing to make an alkyne, you can just make a Grignard reagent and you can stick your 2 things together to make a really complex structure pretty straightforward if you can get to either of the halves of it with the bromides in the right spot. Alright, so once we make a Grignard reagent, we basically just treat that carbon like it's a carbanion. Technically, I would prefer if this was shown like this instead of a lone pair. We actually show that just like we did with the hydride. That's the same net result. And so this is a pretty good way to take a carbonyl and make a tertiary alcohol out of it as well. If we want a tertiary alcohol, we can't just do a hydride reduction, but we can do a Grignard reduction. And so the net result, the way we normally write it, and we don't get great yields with this, but it also means we can do this more than one time. So this actually does work with acid derivatives as well. So if we started with an ester, if we had at least 2 equivalents of methyl magnesium bromide, that makes the methyl a nucleophile. So it's again going to be the exact same mechanism for doing this as with the hydride. We're just adding a methyl group each time instead of adding hydrogen each time. So we make a tetrahedral intermediate, then we kick off the methoxide to reform the what would now be a ketone, and then we'll do it again with another methyl magnesium to break up the ketone and turn it into a tertiary alcohol. So if you want to make a tertiary alcohol, this is really the only way to do it. Because this is our method, I guess, other than you could do an SN1. with hydroxide as your nucleophile, but there's a whole lot of other competing reactions then, right? The trouble with Grignard reactions seems like this is sort of a magic bullet. The trouble with it though is that Grignard reagents aren't super stable long term. They'll react with water in the air. And you wind up making with them getting oxidized and just turning into the alcohol version. And you wind up making magnesium oxide and an alcohol out of your Grignard reagent. So a lot of times, so you can't buy, I guess you can buy Grignard reagents, but it's not commonly done. Usually if you're gonna do a Grignard reaction, you're gonna make it in-house. And then you're gonna turn around and use it within the next 24 hours ideally. When we do this for this class, I think we don't actually get to this lab this quarter. It'll probably be one of the first labs for next quarter. We'll actually make our own Grignard reagent and then use it the following week. But we have to get it really well sealed and keep it really cold to minimize the oxidation. And we still only get mediocre yields out of it when we use it the following week, but we do get product. So that's kind of fun because it's a 2-week synthesis lab where we actually get to make our own reagent and then use it again. Which I always thought was pretty cool.
So then when it says,
Go
when
ahead.
it says excess down there, it just means that like you could have.
At least 2.
Okay.
Yeah. But in general, if we're gonna do at least 2, we might as well do more, especially if it's a reaction where we're worried about the purity of our reagents or equilibrium in general. If it's a reaction that doesn't get great yields, a lot of times having more than 2 equivalents is a way to use Le Chatelier to get yourself another couple % yield on the product side. It doesn't always work, which is why we don't always just flood everything with excess of one of the reagents. Because 1, that gets expensive, and 2, you can wind up with side reactions taking over if you're not careful about concentrations. But a slight excess winds up being really helpful in a lot of ways. When we do this reaction too in lab, we'll actually, the next step after this is then you add water to it. Because what the water is going to do is basically take any of this that's left over and just neutralize it, because it's pretty reactive on its own. It's kind of a nasty thing to have just sitting around, especially if we're going to then try to purify it. It makes more sense to try to purify it where we know what everything is and we don't still have a really reactive molecule floating around. All right, so here's what it looks like for a carbonyl comp. This is the same one. This just has it given twice.
Yeah.
So same basic principle as the producing the carboxylic acid before. You make that tetrahedral intermediate. It's just now we have an R group here instead of an H. It's gonna reform the carbonyl, and your leaving group leaves. So then we made a ketone, and then it's gonna do it again. And I believe this is one where you can stop halfway. If you do 1 equivalent to the Grignard reactant, a Grignard reagent, you could stop at the ketone and then do sodium boryl hydride to turn it into a secondary alcohol. It gets a little bit tricky to make sure everything's purified in terms of practical sense, but that is doable, as I recall. All right. So let's think about it from a synthesis point of view. If we're trying to make, and it's giving you the caveat, you have to use a Grignard reagent somewhere. It's a tertiary alcohol. What could we start from? Both to make our Grignard reagent and to make our alcohol. We have 3 different R groups. So we can't just do excess anything. We could start from a ketone though, what possible ketones could we start from? We could start from butanone. And then. The last R group would have to be the Grignard reagent then, right? Phenols work really well for this though. It's the reason that phenol was specifically called out as one of the examples. Bromobenzene reacts really well to make magnesium bromobenzene. So we see that a lot. What other possibilities though could we use? Basically, there's gonna be how many different combinations could we use? 3, right? We could have, and we could technically start with an aldehyde with only one of our R groups attached. And then do 2 successive Grignard reagents, but it's gonna give us better yields. We can start from a ketone instead of the aldehyde. So we could leave the benzene attached. And have a methyl group. In which case we just need a ethyl magnesium bromide. Or we can leave the ethyl group attached and have methyl magnesium bromide. This is definitely a case where now we have 3 that are all equally valid to the best of our knowledge. They should all give us roughly the same yield. So this is actually where, if we're actually gonna try to make this product, we would actually start by going and looking at the stock room and see what we have. Do we have bromobenzene? If we have bromobenzene, we have butanone, this way makes the most sense. But if we don't have bromobenzene, but we do have bromoethane, we could use this pathway. As long as we have this. Right, so it's just it's a matter of figuring out what do you have. These are both really common reagents though. Bromobenzene, almost every chem stock room in the world has bromobenzene. And if not, when we get to aromatics, that's one of the first things we'll learn how to do is put a bromine on regular benzene. So we can make bromobenzene pretty easily, and butanone is really common too. In fact, if you go, as long as you go to the Nevada side, you can actually go buy this at a hardware store. Just under the name methyl ethyl ketone, which if you ever worked in a paint shop or worked for a painter, it's a really common paint thinner. Also works as an engine stripper for removing grease and stuff like that. And usually you just see abbreviated MEK. If you ever seen MEK on in somebody's garage, it's methyl ethyl ketone, which is better known as butanone. Illegal in California, just like acetone is. Acetone you can get in California, but it has to be produced a certain way. I don't think you can buy MEK in California anymore, but Nevada you can. There's a hardware store on Kingsbury Grave.
Is it still there?
Is it? Did that one close?
I think that one on toast, yeah.
For a while, I couldn't get good solvents when I in California, so I was going to that one to buy xylene in particular. They still say it's sold xylene over there, but you can still go down to Carson City. Lowe's in Carson City has all this stuff too. Not that I would recommend doing that, transporting chemicals across state lines. But if you want the good stuff, actually drain cleaner. Get the good drain cleaner. You still get Crystal Lye drain cleaner, which is really good at clearing out your plumbing. Not metaphorically, literal plumbing. Don't drink the lye. And actually, you can buy concentrated sulfuric acid too. The liquid drain cleaner is 12 molar hydrochloric or 12 molar sulfuric acid. They sell it in a plastic bag, in a really thick Ziploc bag, inside a bottle.
Oh.
So a bottle inside a really heavy duty Ziploc bag, that's how you know it's really dangerous, when even the stores are paying for that extra containment. For OSHA reasons. Anyway. I think the next slide just has these all written out and has it actually color coded so you can see the different R groups. And so you've got your choice of any of these three pathways would work well. And like I mentioned before, with any Grignard reaction, the second step is always going to be add water. Because just like lithium aluminum hydride, you need a proton source to protonate the alcohol at the end. And it has the added benefit of using up any excess Grignard reagent you still have floating around. So that's why it's really common to, if you're going to air, if you're not going to put it 1-to-1 right on the nose, do a little bit excess of the Grignard reagent because we're going to neutralize it in the next step anyway, and that makes it pretty easy to clean up and get rid of. So let's do some more practice with these Grignard reagents. Figure out what you could use. What are your possibilities? And then put a little thought into what do you think might be make the most sense. They're all going to have at least two possible ways to do it, right?
I think this is also.
I think this was a quiz question too. Two options for this first one. And really, if it's a secondary alcohol, we could just start with the with the ketone, if we had two pentanone. We could just start with 2-pentanone and use sodium borohydride. And that actually would probably make more sense. But in this case, because the reaction specifically said Grignard, we're trying to work on it. The only time you have to use Grignard is when it's a tertiary alcohol, or when you don't have either any of these other starting materials or the proper starting materials. So we could say that would give us the same product too, right? In fact, if we have this in the stockroom, this would make more sense. What about B? It's tertiary alcohol. Got two options. Because we have two identical substituents, right?
Yeah.
3 options total. So we could start from the 2-pentanone again. And do methyl magnesium bromide. That's 2 of our options there, right? Or we could start from acetone. And do, that would then be 1, 2, 3 propyl. Yeah. Is there a better option for this one? Or another option? We could do start with butanaldehyde. And add 2 methyls to it. We could do the same reaction twice to excess magnesium. Right, if we started here. Chopped off both those, then we could do the same reaction twice to add 2 methyls to it, since they're the same. If we have methyl bromide, there's no difference between this step and doing it twice. If they're identical, sometimes that actually make more sense because it's doing the same reaction twice, which means you don't have to stop and purify it in between. Because you could still just dump twice as much methyl magnesium bromide in. So if we had this but not that, for instance, it would make this on its way to making our final product.
Wait, would that possible, because after the first reaction, it would make a secondary alcohol, so it'd be too.
Oh, you're right. You're right. You can't do that. That would work if we started with the butanoic acid.
Yes.
There we go. Because we have to have 2 oxygen bonds we can break in order to do that. And the more I'm thinking about this, the more I do think you can stop halfway through with these Grignard reagents. You can do 1 Grignard reagent, let it react, and then add a second different Grignard reagent. If you're starting from a carboxylic acid, so you can actually start from this and add 2 different R groups to it. It always would be easier to just start from the ketone if you have the right ketone. But if you don't have the right ketone, starting from the acid and adding 2 different Grignard reagents is another way to do it. Or do 1 Grignard reagent followed by sodium borohydride. So, and this winds up being something that in a lot of organic synthesis labs winds up being a big part of your actual project or your research is not just the last step or to get your final thing, your final synthesis. sometimes you'll need to actually start from a material that's not commercially available. Which means you've got to synthesize your reactants that then you can actually do your final couple steps with. So making your own reagents in-house winds up being kind of a big deal sometimes, and this is a really powerful way to do that. If you were doing this as your full-time job, then you could do a Grignard reagent, you purify it, use your Grignard reagent in the same day to make something that then you could purify and use, and that's the next step in the reaction pretty well. We're limited to only 3-hour labs here, because this is not your full-time job. But that's pretty common. You can actually do a couple of these back to back to back. And then you would spend the next day just doing the purification for that before you go into your next synthesis day. If you like being in lab, there are worse jobs than being a synthetic organic chemist, because it's a lot of spend a day planning it out, spend a day getting all your reagents set up, make your own reagents if you need to, and then go and try and make something that nobody's ever made before for some pharmaceutical purpose or some material science purpose. All right. Last one. If we're gonna use a Grignard reagent for this, what do we have to start from? Got to start from formaldehyde. We only have one R group attached to our carbonyl, right? Which means we had to start from formaldehyde, which from a practical sense has its own set of issues. Usually when you buy formaldehyde, it's actually in a solution with alcohol or with water. And it actually goes through an equilibrium reaction where it makes the methane diol. And it goes back and forth, because that's not a oxidation or reduction. This will constantly be, if you're in, they call the solution formalin, is the way that you can normally buy it. And it's a protic solvent. And so basically we'll constantly, it's almost like an enol polymerization. We wind up with this. Reacting back and forth in equilibrium all the time. So formaldehyde is actually not commonly used in organic chemistry as a reagent, because it actually mostly present as this. They didn't know that when they first started calling it formaldehyde, when they first in the 1800s, when they were using formaldehyde to preserve specimens, they didn't realize that they were actually preserving it with this. So they called it formaldehyde, thinking it was this. So, but all that aside, there's a reason we don't see formaldehyde as a reactant very much. This is like one of the very first times we've seen that as a reactant in either of these classes, right? And that's why. And because if you try to get it away from a protic solvent, this is a gas at room temperature. So then you're dealing with the gaseous reactants. You can keep it as the formaldehyde, but only if you're going to keep it as a gas. So either way, if we're trying to do this though, then we just have our propyl magnesium bromide again. So propyl bromide could be used to make all three of these. We just want to make sure it's one propyl bromide. And then literally the process for reacting it is you take solid magnesium violins and you dump, if you started from propyl bromide, bromo propane, you just dump magnesium turnings, they're called, little chunks of magnesium into the bromide. You just let it react. And then you actually will get a solid out of it. You get a white powdery solid that you can recrystallize and purify, filter out. And then you wind, and that's your magnesium bromide, your propyl magnesium bromide.
Is that what they do with the like lathe waste from when they like lathe magnesium and stuff? Is that why it's called turnings?
Just probably, actually, because they do tend to have like a little, the shape of them is a, yeah, it's almost like yeah, like something like wood shavings.
Yeah.
So maybe they use that.
When you like machine magnesium, it comes off in a really long coil.
Yeah.
Yeah.
Yeah, probably the stuff that we're getting in from chemistry suppliers, you'd have to do that in an anoxic environment because magnesium oxidizes so well. But if you did that, you could make magnesium ribbon, they call it, is the other thing that you make. If you did that in under argon or just pure nitrogen, you would wind up with magnesium metal turnings or magnesium metal ribbon. So yeah, probably that's how they make it. All right. We're done early again today, which means if you have any other questions, now is a chance to ask them about any of this stuff. I think we've laid the groundwork pretty well, though. Right, our two new mechanisms are hydride reduction and Grignard reductions.
And they're both kind of the same.
And they're both kind of the same thing. It's just what metal do you use? Right? Are you adding an R group or are you adding a hydrogen?